Hi, in this video we will learn about a new notion, subspaces of Rn. These are a collection of vectors in Rn which satisfy some conditions, and we will study these conditions for some examples. Okay, let's dive into this and see what is a subspace of Rn. So a collection S of vectors in Rn. So you pick bunch of vectors in Rn, put them together. The collection of this Rn is called subspace or linear subspace. Sometimes people call linear subspace of Rn if it satisfies these conditions. First of all, the zero vector is in S. Whatever else you have, you put it, just forget those ones, but zero should be there. The second one is it's called closed. S is closed under addition. What does it mean, being closed under addition? It means that if we have two vectors, u and v in S, then the sum of u and v is also in S. So then u plus v is also in S. So you add any two vectors in S, you will get back to S. So you will get a vector which is in S. That's what means being closed. Also, S is closed under scalar multiplication. Means what? Means that if a vector you pick from S, then any multiple of that, Cu, is also in S for any scalar C. So you multiply any vector in S by any scalar, it will give you some vector which is again in the S. So it is closed under scalar multiplication. Some people, instead of using these two, they say put one condition. It is, so let me just do second prime. And they say S is closed under linear combination. It means that if you pick any two vectors, u and v are in S, then you can conclude that any linear combinations of u and v is also in S. So C1u plus C2v is in S for all C1 and C2. So all linear combinations are. So that is equivalent actually to this condition. So let me just do this thing. It is equivalent. We will when we studying subspaces, we will do all three separately. Okay, so it's time to do some examples. Let me copy paste all the examples I have here. Okay, we have to check if some sets are subspaces or not. So let's just go one by one. determine if the given vector, the given sets are subspace or not. S1 is the set of all unit vectors in R2. So we are dealing with basically all vectors xy such that the length of the vector, which is x squared plus y squared square root, is equal to 1. Well, let's start with the first condition. First condition, is 0 a unit vector? And right away you notice that length of 0 vector is 0. It is not 1. So 0 vector is not unit vector. As a result, 0 is not in S1. So right away, it means that the first condition fails. And you can conclude that S1 is not a subspace or a linear subspace. But let me just show in some examples that, by some examples, that S1 is not closed under, well, both of the operations actually under addition. Let me show some example for this. These are counterexample basically. So if you have 1, 0, this is a unit vector, and 0, 1, this is also a unit vector, are in S1, yes. But when you add them, so you add 1, 0 plus 0, 1, what we get is a vector 1, 1. But when you find the length of that vector, why do I find the length? Because I have to show that the length is 1 or not. Length of this guy is 1 squared plus 1 squared. The square root, this is the square root of 2. This is not 1, so that means that u, the vector u, and vector v were in S1, but u plus v is not in S1. In other words, we found two vectors. When we added, it was outside S1, so it is not closed under addition. And for the scalar multiplication, for example, you multiply 2 to one of these vectors, you see that the length of this vector, which is 2, 0, is 2 squared plus 0 squared, and this is 2, and obviously it's not 1. That means that 2 times u is not in S1. So scalar multiple of a unit vector, actually any scalar multiple other than negative 1, 1 will be a vector which is not unit. So it is not badly not satisfying all three conditions actually. Okay, how about this one? So we are trying to see what kind of, so these are all vectors, so xy in R2, whose first component, so x, is twice as the second component. Very nice. For example, this has something like 2, 1, yes, or something like well, 4, 2, or as you can see. So we have to check all the conditions. Is 0 here? So 0, 0 vector, the first component, so x here is 0, and y is also 0. You multiply y by 2, you get x. So 2y is equal to x. That means what? That means that 0 vector is in S2. And we have at least the first condition so far, yes? How about the second condition? Okay, so we are taking two vectors. Let me say x1 y1 and x2 y2, and we want to we take these ones are from S2 or in S2. Well, it means what? It means that x1 is twice as y1 and x2 is twice as y2. Now we want to check if their addition, which is just x2 y2 and this guy x1 plus x2 y1 plus y2, is the first component twice as the second component. Well, you see that if I add these equations, I'll get x1 plus x2 is going to be 2y1 plus 2y2, which is the same thing as 2y1 added to y2. This is the first component of the addition. This is the second component of the addition. And we showed that the first component of the addition vector is twice as the second component of the addition vector. So it means that yes, S2 is closed under the addition, And let me do the third condition. How about a closeness under the scalar multiplication? So we always start with the vector x1, x and y is in S2. Means what? Means that x is twice as y. Then we want to see if now if I multiply this vector by a scalar, what does scalar multiplication do? So you multiply that scalar to all the components. Then we know that here Cx is, well, we already know x is twice as y, and this is the same thing as writing 2 times cy. What we showed was that the first component of the scalar multiple of xy is twice as the second component of the scalar multiple. That means that S2 is closed under scalar multiplication. And well, that means that yes, this is a linear subspace or just subspace of R2. Okay, S3, the first quadrant, all the vectors whose components are non-negative. In other words, we are dealing with vectors x, y such that x is bigger than equal to 0 and y is bigger than equal to 0. Well, obviously, 0, 0 is in S3 because 0, the first component, and second component, both of them are bigger than equal to 0. So yes, it is in R2. How about closeness under the addition? Okay, here, so let me just give us a little bit more space. So again, we start with 2 vectors, and x2, y2 are in S3. Means that i.e., not e.g., i.e., that means that x1 is positive, y1 is positive, x2 is positive, y2 is positive. And from this, you can conclude that x1 plus x2 is positive. You're adding two non-negative numbers, you will get a non-negative number. And y1 plus y2 is non-negative. From here, you can see that these are the first component and second components of the addition vector, and it is in S2. So yes, S3, sorry, we are studying S3 here. So this means that S3 is closed under addition. How about the third one? Okay, third, is it closed under the scalar multiplication? Well, for example, if you take two components, a vector from this from this S3, so is in S3, it means that x and y are positive or 0. Then, for example, if you multiply this by a scalar like x by 2, you're good, because x is positive, you multiply it by 2, which is positive number, you get positive or 0 number, and 2y is going to be positive. But scalars can be negative numbers, so you can multiply this by a negative 2. This is a scalar, yes? And when you multiply something which is non-negative by a negative number, you will get something which is not anymore non-negative. So both of these guys are going to be 0. It is not closed under the scalar multiplication. Not close. Not closed. So it is when you take a vector, when you multiply by negative scalar number, you may get something which is outside this guy. Okay, S4 is okay. So first condition, 0, 0, 0. The vector 0. This is on R3, and you see that the first component x, which is 0, equals the second component, which is 0. Yes, so that is correct. And the first component, the second component 0 times 0, that's also, so that means that 0 vector is in S4. How about addition? Okay, so we do again, we pick two vectors, and x2, y2, z2 are in S4. Then what you do, you just add them, and you see, well, first of all, this is in S4 means what? Means that x1 is equal to y1, and y1 is equal to z1. Also x2 equals to y2, and y2 is equal to z2. Now, if you add these equations, you get x1 plus x1 plus x2 is equal to y1 plus y2, and you see that y1 plus y2 is equal to 2z1 plus 2z2. Factor 2, you get z1 plus z2. But what are these guys? These are the components of two vectors that we started from the beginning. So it is basically addition of x1, y1, z1, and x2, y2, z2. So this means that yes, it is the addition is in S4, so it is closed under addition. How about close under scalar multiplication? I'll take this one. You multiply this by a scalar, so it will give us cx1, cy1, cz1. And since we know that x1 was equal to y1, that means that cx1 is also equal to cy1. And we know that y1 is twice as z1. So if you multiply it by c, that means that you have cy1 is also 2 times cz1. As a result, that means that if I call this guy u, it means that cu is in S4. So that means that S4 is closed under scalar multiplication. Okay, so it was closed under everything. So this is, yes, a subspace of R3. How about S5? S5 is a set of all vectors in R3. So we have X, Y, Z such that the third component is equal to 1. Okay, start with the first condition. Is 0 vector such vector? So 0 vector is 0, 0, 0. The third condition, the third component of 0 vector is 0, which is not equal to 1. That means that 0 vector is not in S5. You can also show that this set is not closed under addition. It's not closed under scalar multiplication. So I'll leave that one for you, and that is enough. So for the first one, not satisfied, is enough to say that S5 is not a subspace of R3. So you see these three conditions. We will work with these subspaces more and more, but you have to be able always to check the conditions which needs to be satisfied for subspaces.